So now we will discuss about some problems associated with the transformers. And one problem is the problem of harmonics, and second problem is the switching transient, which actually causes high inrush current. Okay, so let's see how actually these things happens in a transformer. So we know that when we energize a transformer, when we energize the transformer to magnetize the core, even at no load, the transformer draws, the winding of the transformer draws some magnetizing current, right? And we have seen that the magnetizing current, since we operate the transformer, if you see the BH characteristic of the transformer, so this is, let's say, B and this is H. So generally we operate at the knee point of the transformer. So beyond that the core gets saturated, right? So what happens is, once we operate at these points, because we want to utilize the transformer fully, the core material fully, we design in such a way that we try to operate at this knee point, right? Because of this BH characteristic, if you see the current is not exactly sinusoidal. Rather, it has some high frequency components in it as well. So if you see here, this is the fundamental voltage current, magnetizing current of one phase, and this is the actually the harmonic component into it, and this is the actual magnetizing current. If you'll see, this is the actual magnetizing current, and this is actually IM1, I would say, and this would, I would say, IM3, which is the third harmonic component. Even fifth harmonic component is also there, but main concern is because of this third harmonic, so that's why I'm discussing it here. And if we write the magnetizing current for each phases, so let's say IMA, if I write, it would be IM1 plus IM3. And if you see the expressions of it, it would be actually IM1, or I would say IM1 sine omega t, and the third harmonic component is actually IM3 sine 3 omega t. Similarly, for the other phases, if I am writing, let's say IMB, this would be IM1 sine omega t minus 120 degree. Since I said all the phases are balanced, but in a single core transformer, I said these current would be actually different. The magnitude would be slightly different, but at load condition that doesn't matter. Okay, sine 3 omega t minus 3 into 120 degree. And if you see IMC, that would be again IM1 sine omega t minus plus 120 degree, and this would be IM3 sine 3 omega t plus 3 into 120 degree. Okay, so now in star-star connected transformer, okay, star-star connected transformer with neutral open, this is a serious problem there. The reason is, in a star-star connected transformer, what would be IM1 plus IM2 plus IM3? If you see, if you sum these component, this will come out to be 3 times of IM3 sine 3 omega t. Okay, see, because 3 into 120 degree itself is 360 degree, and 3 into 120 degree is 360 degree. So if you see these three, this quantity, and this quantity, they are cophasor. Okay, cophasor. They are cophasor. Okay, that's why the sum of it won't be 0, right? But in a star connected transformer, let's say the winding is this, the sum at this node, the sum of all these 3 current at this node should be 0. Otherwise KCL would be violated, right? So my transformer is actually not allowing this current. If this is only star, neutral, open means no, it has not been grounded, then this current cannot flow here at the node, right? Because at this node, sum of these three currents should be 0. That's why in a star-star connected transformer, the magnetizing current, I would say, is actually perfectly sinusoidal, okay, for each phases. And if it is perfectly sinusoidal, then in that case, it is 0. Now, if current is perfectly sinusoidal, the BH curve actually demands that the flux will have this third harmonic component there. And since the flux is having the third harmonic component there, the induced voltage at the secondary of this transformer would be, will have actually the third harmonic component there. They would be perfectly, they would be having third harmonic component. So in a star-star connection, the magnetizing current is perfectly sinusoidal. So this actually results in harmonics in the voltage, in the induced voltage. Okay, so actually this kind of arrangement we don't prefer in the power system network. If we want to, then what are the solutions? The solution is either, there are two solutions. Either we ground the neutral, either we ground the neutral point. Okay, that means this is actually grounded. This is actually grounded. Either of the side will also work actually. Okay, so ground the neutral point. Second solution is using tertiary winding. So actually what happens is, if let's say one of the winding is delta, so here actually this delta connected circuit actually forces the primary, because in this we can have the circulating current. Okay, so the magnetizing current, which was actually not forced here in this winding, was actually allowed in the secondary of the transformer. That means in this secondary side there is a circulating current, and this circulating current is nothing but IMA plus IMB plus IMC. So circulating current actually flows in the delta connected winding, and since this current is flowing in this delta connected winding, the current is actually drawn from the phase as well. So in the line you would be having the harmonics, but well, in the primary side also now it would be the harmonics would be present, because there is a circulating current here in the secondary of the transformer. So this is one of the technique, that if I want to use a star-star connected transformer, then in that case what is generally done is, either the ground is a neutral point is actually grounded. Other way is to use a tertiary winding as well. So star-star, and another tertiary winding is used, which is not actually the power, I would say the power transformer, rather the simpler winding, which can actually handle the circulating current here because of the harmonics, as well as the current which is unbalanced, current which is caused in the, so the unbalanced current which was forced because of the unbalanced load, so that current is also flows through the tertiary winding. So like instead of dumping this entire current in the ground, it is now forced in this tertiary winding, and this tertiary winding is used for auxiliary supplies within the substation as well. So this is one of the technique as well, if I want to use the star connected transformer. Otherwise mostly the transformer which is used is star delta or delta star. And we'll show you one experiment. Before going further, we'll show you one experiment where we have discussed this, that in this experiment what we have done is, I have taken a 3-phase transformer, single core 3-phase transformer. Okay, and the primary of it is actually star connected, and we have energized it by a 3-phase source. Okay, 3-phase source. It was energized by a 3-phase source, and at the secondary of it, what I have done is, I have just connected a delta connected circuit. This one, and this one. And between these two terminals, I have not shorted it, but between these two terminals, what I am doing is I am just measuring the voltage. So let's say if this is A1, A2, or I would say, let's say this is A1, this is A2, this is B2, this is B1, and this is C2, this is C1. Okay, and the voltages are as per these dot connections. So obviously we have seen in one of the delta connector in one of the previous lecture that the voltage here, if you'll see, if it is a perfectly delta, this should be 0, right? Between VA2 C1 should be 0, right? But you will see that obviously the fundamental component is 0, but in this kind of condition you will see that there would be a because the neutral is not grounded here. Since neutral is not grounded, the voltage will have the third harmonic component into it, and since the voltage is having the third harmonic component into it, the sum of it, if you'll see, is actually I would say, let's say VA, the sum of it won't be 0. Okay, then what we did is, in the second part of that experiment, we actually grounded this terminal. Okay, and before grounding, and before that, what we did is we were observing these currents here in these branches here, and we were using a current probe to sense this current. Obviously, if I'm sensing this current, the sum is 0. That means IA plus IB plus IC is actually 0, right? And here the voltage is actually not 0. You will get some voltage which will have third harmonic component actually. Okay. So then in the second part of this experiment, what we did is we have shorted this terminal, okay, to show that the sum of these voltages will be actually 0. That means there is no third harmonic component here, because third harmonic component is actually the phasor component, right? Co-phasor. Let's say the voltage is here VA1, I would say, and plus VA3, right? Similarly VB1 plus VB3, similarly VC1 plus VC3. Some of these voltages at these terminal, if you'll see, that will come out to be VA1 plus VB1 plus VC1 plus 3 times of this voltage, let's say V3. V3, I would say the third harmonic component, V3 I would say, right? So, and obviously the sum of these 3 component is actually 0, but this component still is there. So that's what the experiment is. But once we have grounded it, then you will see that the sum of these current is actually not 0, and that will come out to be in the second experiment. In the second part of this experiment, let's say if I have grounded it, then this IA plus IB plus IC is actually not equal to 0. Rather, it is some IM3, 3 times IM3, some magnitude in the third harmonic component. And if you see the voltage now, VA2 C1, so if you see this voltage, this would be 0. That means if I am allowing the magnetizing current somehow to pass right in the network, then the voltage is perfectly sinusoidal, third harmonic component is not there. And if I am not allowing the magnetizing the third harmonic component of the magnetizing current to flow in the network, then the voltage waveform gets distorted actually. Okay, it will have the third harmonic component. So in this experiment, what we are doing is we have connected the primary side as a star connected one. Okay, and this current probe is actually sensing the current, the sum of all these 3 phase currents. You can see here that all these 3 wires are passing through it. So obviously it will sense all these 3 currents, and obviously it will come out to be 0. Let's see. And the secondary side, what we have done is we have connected into delta. So you can see here from this terminal till this terminal, it is a delta connected one. See here. But The third phase I have not connected, rather I am just measuring the voltage here. So if you see the voltage here, like between this terminal, the very first, this terminal and this terminal, if you'll see, the sum of it should be 0, right? Because on each phase you have VA plus VB plus VC. But if you observe here, we have already energized it, and if you will observe here, this is the voltage, yellow one is the voltage waveform and blue one is the current waveform. So current, you can see that it is almost 0, means it is 0 only, and you just focus on the frequency component there, the cursor point. Okay, so these two cursor, if you see the differences between it, the frequency is coming around 149.3 Hz. That means this voltage signal is actually the third harmonic voltage component. So line voltages has cancelled out, but the cophasal, the harmonic component in the voltages, third harmonic component, they are cophasal and they does not get cancelled out, and we see the voltage there, and net voltage would be there, which is the third harmonic component in the voltage. Now what we will do is we will short the neutral of this star point through a wire to the ground there. Okay. So though we are doing it online, but it's better to remove it, right? So you see the voltage waveform, there is no harmonic component in it, right? It is almost 0 here. Okay, but you see there is a current component now. And if you again see the harmonics there, you will see the frequency of it would be around the same as the third harmonic component. This magnitude is not 0 now. The current has, because this you are observing the sum of the current, right? IA plus IB plus IC, and they have the harmonic component as well, and this is not 0 here. Okay, thank you. Now we will discuss about the switching transient in this three-phase circuit.